All right, guys. So in the previous video, we talked about the light bulb or the light sources that are required for the instrument to work. And we said that the old school versions have a tungsten bulb and a deuterium bulb. However, nowadays we typically have just one bulb that will do them all, and that one bulb is a xenon arc bulb. All right, so now we're going to move on to the next piece and part, and that next piece and part is going to be our monochromator. I'm going to do this one first before I talk about the cuvette holder. Again, sometimes the monochromator is afterwards, sometimes it's before. However, in the old school versions, and probably what you'll see me do in the PowerPoint and by just creature of habit, is that I do put the monochromator in the beginning. It just I think makes sense to me more in the beginning, but for some reason they're starting to play around with the location of the monochromator. And whether it comes before or whether it comes after, it doesn't really make a difference. It's still going to do its job the way that it needs to do its job. Okay? All right. So the monochromator has a specific function. And the monochromator, mono, if I look at this word breakdown, means one, right? And then if I look at the word chroma, chroma basically means color. So monochromator literally translates to one color. All right, so let's kind of think about this for a minute. If I have a light source and that light source is giving me light for my sample to absorb, then this has no way of separating 200 nanometer to 201 nanometer, right? The light source cannot separate. The light source can give off all wavelengths. That's all that it can do. And the reason that it makes sense for the monochromator to be here in the beginning is that the monochromator will take all of the wavelengths from the light source and it begins to separate them. And when it begins to separate them, it's able to basically pick out one lambda that you will use to measure. So again, what goes on is that the light source gives off, if it's a deuterium bulb, 200 to 400 nanometer. And all of that basically goes onto the monochromator. And the monochromator will go through and it will dial in very specifically. And it will let me to hone in on just one lambda if that's what I want to target. So instead of the whole range of 2 to 400, I will tell it I want you to go to 274 nanometer. And that is the piece that allows the instrument to dial in to 274. It is the monochromator that does it. Now, the monochromator can be different specialties. We have monochromators that can give me just whole number, 274, 275, 276, 277. But the sensitivity of the monochromator can be changed, and we can actually do a wavelength with a decimal after it. So I can actually dial into some of the machines and do 274.5 nanometer. That all relies on the resolution of the UV vis spectrometer or the instrument, okay? So that's the purpose of the monochromator. Now, if I go through and kind of take a look at what the monochromator looks like on the inside, then this is a diagram that we typically see. Now, what on earth does that mean? All right, well, let's start at point A right here. Point A is the light source, and that light source is all coming into the monochromator. So this point B is basically the doorway in. So once the light goes through the doorway, it is now in the monochromator. And this light basically hits a mirror at C. All right? And C will basically take the light that gets shown into the box and it deflects it or reflects it. And then it points it to what we call part D, the grating. And the grating is what makes this monochromator work. So if you look at the color of the arrows, these are white. and we often call it white light. So this is all of the nanometers all at once going into the monochromator. It hits the mirror reflects it and bounces it off, and it shines it and directs it at the grating, which is really the monochromator at work. The grating, if you look at the diagram, have these little slashes in the diagram. Okay, those are teeth. And these are very fine etches that's inside of the glass. So someone has taken this prism basically and has etched it and scored it a number of different times. And depending on the number of lines or the etching that's there, the monochromator can separate more and more and more and more. And that's how we go from whole numbers down to partial wavelengths. It's due to the actual number of teeth, is what we call it, the teeth of the grating. So the white light comes onto the grating, and if you now notice, the white light is getting separated into all of the colors of the rainbow. And that's why you're seeing the arrows now drawn blue, green, and red. So the grating reflects it and bounces it back to another mirror, and that's for E. And then that mirror basically sends it out of the box. So F is the exit doorway, out of the box and onto the sample, which would be at G. And notice that only the green light is allowed to come through because that's how I've kind of tuned in my instrument. Maybe that's the only lambda that I want, and it just so happens to be green that's coming out of the monochromator itself. Now, you know as good as well as I do, the monochromator doesn't really look like this, right? This is just a diagram or a depiction of what these things actually do. So white light comes in, bounces off a mirror, goes to the grating. The grating has these little teeth in it, and those teeth separate into the individual wavelengths. Those individual wavelengths get shown to another mirror, and then it finally tunes that mirror and only allows one lambda to come through, and that's it. So what do these things really look like in person? This is a monochromator, people. This is the diagram, and this is what it's trying to represent. So inside of this box, you see a mirror that's basically right here. So this mirror is basically either C or E in this diagram because you've got to have something that bounces the light around in once you make it inside of the monochromator box. Once the mirrors do their job and direct it toward the monochromator, there's probably some on the back side of this as well for it to shine in and then bounce back. This big plate here, it almost looks like it turns. Do you see that there at the very bottom? It almost looks like there's a gear right there. That gear will allow the monochromator to turn back and forth. And that's basically what needs to happen when the monochromator picks one wavelength to shine into the machine. So this is the area that has the etching in it, and this is the area that has what we call the teeth, right? The etching. And that allows the white light to be separated into the individual wavelengths. And to help matters even more, then this thing can rotate. And if this rotates, we can finely tune the instrument to only give me one lambda, and that is it. So once it does, it will probably bounce it off to another set of mirrors, and then those mirrors will bounce it off out of the monochromator box itself. So that's what a real monochromator looks like, and that's what goes on inside of the monochromator, or what we call the black box of the machine. So all monochromators have to have the same kind of setup and the similar pieces, and they have to have an entrance slit to come into the black box. They have to have an exit slit that allows the light to go out of the black box. They have to have a series of mirrors. It could be 2 mirrors, it could be 4 mirrors, just depending on how that monochromator is set up. That can vary and change depending on manufacturer. And it has to have a grating, and this grating again is the piece that has all the teeth on it, that or the etching that allows the white light to be separated off into its individual pieces. So these are the pieces that are required for all monochromators. And the most important piece, of course, is the grating. And if we look at the grating, this determines the resolution of the instrument. So the more grooves or the etching or the teeth on the grating, the better the resolution. And the resolution is its ability to separate the individual wavelengths. So can I only go to 274 to 275, or can I allow the machine to go to 274.1, 274.2, 274.3, 274.4? Or can I allow the machine to go 274.15, 274.16, 274.17? How many decimal places can I actually get this wavelength to go to? That's the resolution of the UV Vis instrument. All right. So this is what rotates inside of the machine, and we call this whole process of taking light and dividing it up into its individual pieces the concept of diffraction. So that's what diffraction means when it concerns light. Can I take a light source and can I break the light up into individual wavelengths? And that diffraction is the process that we use to describe uh, that whole concept. All right. So that's the purpose of the monochromator. And again, in some diagrams, you'll see it here at the after the cuvette cell, and in some diagrams, you'll see it before the cuvette cell. And honestly, and preferably, I like to see it before the cuvette cell. It seems that this is still basically the way that some of these are set up. Some of the new ones are wanting to put it over here, and it doesn't really make sense. Maybe they know something that I don't, but it just looks like the monochromator would work better here before it goes into the cuvette holder that's there. All right, so light source, tungsten bulb, deuterium bulb. That light source provides all the wavelengths to the monochromator. The monochromator then will use the grating, and it will rotate the grating to select one wavelength, and that's it. And that one wavelength gets presented to the cuvette cell that has your sample in it. So in the next video, what we'll do is that we will go on and we will talk about now the cuvette holder and maybe some things that I need to remember when it concerns the cuvette in a UV vis spectrometer. So our job's not yet done, but we're getting closer and closer. So again, don't go off too far. Just go take a potty break. That's all that we need you to do. And then come back and learn all about the cuvette holder.